All right, hello everybody. Welcome to the first lesson of Unit 3. Today we are focusing on intermolecular and interparticle forces. We are going to focus on how intermolecular forces, which happen between molecules, affect physical properties of substances like boiling points and solubility. You're also going to learn how to connect what's happening between particles to what we observe in the real world. And we'll also look at how the strength of these forces changes depending on whether the molecules are the same or different. And understanding these interactions are going to help us explain why materials behave the way they do. So I introduced this chart to you in Unit 2. And in Unit 2, we really focused on intramolecular forces, which are the forces happening within or inside molecules. Today, we are going to start our intermolecular forces unit, which is all about the interaction between molecules. Now, when we're talking about the strength of intramolecular forces versus intermolecular forces are going to be much stronger. However, we are going to be focusing on intermolecular forces, and even though they are weak compared to intramolecular force, there are still stronger versus weaker intermolecular forces. So the ones on the right in the green, hydrogen bonding, dipole-dipole, London dispersion forces, those are the ones we are going to be assessing this unit. So before we move on, I wanted to give you some items to add to your notes. Honestly, just looking at these and reading these is just going to help you understand all of these intermolecular forces before we start diving into them. So when particles have weak intermolecular forces, they separate more easily, leading to a low boiling point and a high vapor pressure. And a high vapor pressure just means that they evaporate quickly. In contrast to that, strong intermolecular forces are going to hold particles together more tightly, which is going to give a higher boiling point and a low vapor pressure. Remember, in our last unit, we talked a lot about how if you have a stronger bond between two substances, it's going to take more energy to break it apart. So that's why something that is held together more tightly is going to have a higher boiling point. If two substances have similar intermolecular forces when we compare their masses, heavier molecules are going to tend to boil at a higher temperature. And all of these general rules are just going to help us predict how substances behave based on their molecular structure. All right, so first let's talk about London dispersion forces. You will also hear me call these LDFs. Just please note you cannot write LDF on an FRQ. You actually have to write out London dispersion forces. So what London dispersion forces are a temporary shift in electron clouds that create temporary dipoles. So if we're looking at these two neon atoms on the screen here, they start out as just an normal neon atom with its 10 electrons surrounding it, and they're all kind of sporadic. Well, what London dispersion forces are essentially all of these electrons in neon's electron cloud are going to move to one side of the atom and create a negative side of the atom, while the other side assumes a positive side. And because they have a negative and positive side, all of these atoms surrounding are going to attract the positive end to the negative end. So that would be a London dispersion force. Now, when we're talking about London dispersion forces, you'll probably hear the term van der Waals forces stuck in there. Van der Waals is a type of force. It's kind of like an umbrella term that includes LDFs and dipole-dipole, which we'll get into in a moment. But I just want you to know that in case you come across that term. One thing that is really important with LDFs is as you add more mass or more electrons to an atom or a substance, you're going to have stronger London dispersion forces due to something called polarizability. Polarizability is the tendency of molecules to generate induced electric dipole moments when subjected to an electric field. So the larger the electron cloud or the more molar mass, the higher the polarizability. So if we look at this example here on the right, iodide ions with a radius of 220 picometers are much more polarizable than fluoride ions at 133 picometers. That's because iodide has a lot more electrons than the fluoride ion, and because it has more electrons, when it creates that dipole, it will have a stronger negative side, which means it's more polarizable. So to put this in perspective, we have the iodide ion on the left there in yellow, and we have the fluoride ion on the right there in white. Now, those are just the ions without a dipole right now. Now, if we were to introduce an electron field, essentially what would happen is all of the electrons would move to the side of the positive charge in the electron field. And that would create your dipole. And you can see with iodide, we have a lot more electrons to form that dipole, where fluorine only has 10 electrons. As you can see, the iodide ion has a lot more electrons, so it creates a lot stronger of a negative end than the fluoride ion does. And that reasoning when you are doing FRQs for AP chemistry is polarizability. All right, so let's do a practice question on London dispersion forces. The table below provides information about 3 of the noble gases, neon, argon, and xenon. Neon has a much lower boiling point than xenon. Explain. So if we're looking at the boiling point of neon versus xenon, we can see that xenon is much higher. And if we're looking at noble gases only have London dispersion forces because they are not polar molecules. Now, when we are talking about London dispersion forces, remember what increases those forces is our number of electrons or the mass of the substance. So looking at neon, neon has 10 electrons while xenon has 54 electrons. Now, obviously this means that xenon has a much bigger electron cloud, which is more polarizable. And when something is more polarizable, it means that it has stronger London dispersion forces. So since it says that neon has a much lower boiling point, we first need to state that noble gases only have London dispersion forces. Then, since we are specifically referring to neon, we need to state that neon's electrons cloud is much less polarizable because it has less electrons. Therefore, its attractive forces are weaker than xenon, which is why it has a lower boiling point. After London dispersion forces, we have something called a dipole-induced dipole. And what that means is we have a polar molecule mixed in with a nonpolar molecule. And so we have a weak attraction that results when a polar molecule induces a dipole in a nonpolar molecule, making an arrangement of electrons in the nonpolar species. So for example, if we're looking at an oxygen molecule, if it's isolated and only with nonpolar substances, it's going to look like the picture on the left. There is not a negative end or a positive end. It is just a neutral atom. There is an equal sharing of electrons because it's nonpolar and it has the same electronegativity difference. However, if we put oxygen gas in a sample of water, water is a polar molecule, which means it has a negative end and a positive end. And when we put that oxygen molecule in with water, that dipole of water is going to create a dipole in the oxygen molecule, which is where the dipole-induced dipole comes from. So in order to have a dipole-induced dipole, we have to have a polar molecule and a nonpolar molecule in the same mixture. Then we have dipole-dipole interactions. This can only happen with polar molecules. So if you were looking at a substance that is nonpolar molecules, all that can have is London dispersion forces. It cannot have dipole-dipole interactions. So the interaction is going to depend on whether the molecules are polar, and it's going to depend on the magnitude of those dipoles. So for example, if we have a stronger dipole, like in hydrofluoric acid, we know that fluorine is very electronegative, so that fluorine has a strong negative dipole. Now with HCl, it's still a polar molecule. However, that negative end of chlorine is not as strong as the negative end of fluorine. And generally speaking, dipole-dipole interactions are going to be stronger than London dispersion forces. But just keep in mind, if you're looking at two molecules, a small molecule with dipole-dipole interactions and a large molecule with only LDFs, usually the LDFs are going to trump the dipole-dipole just because of that polarizability in that large molecule. So just keep that in mind. So let's look at this example between butane and acetone. So looking at their molar masses, they have the same molar mass, which means they have the same number of electrons. And because they have the same number of electrons, their polarizability is pretty much equal, meaning that we are not comparing London dispersion forces for their difference in boiling point. Instead, we need to look at the difference in intermolecular forces between these molecules. So first, looking at butane, those are all carbon and hydrogen atoms, which we know are all nonpolar, which makes butane a nonpolar molecule. So butane only has London dispersion forces. Now looking at acetone, we see acetone has a double bonded oxygen in the middle of the molecule. And because it has an oxygen, which is very electronegative, it's going to create a dipole, which means it's a polar molecule. And because we have a polar molecule, this means that we have London dispersion forces, because remember, everything has London dispersion forces, and dipole-dipole interactions. And because acetone has London dispersion forces and dipole-dipole interactions, the attraction between acetone molecules is going to be a lot stronger, which is why our boiling point is going to be much greater than that of butane. Then we have ion dipole forces. So these are present when we have a mixture of ions and polar molecules. So for example, when we take sodium chloride and we dissolve it into water, we now have all of these water molecules, and then we also have sodium cations and chlorine anions. And those cations and anions are going to interact with the negative and positive ends of water molecules. So now we have our strongest type of intermolecular force, which is hydrogen bonding. Hydrogen bonding is only going to occur if you have a hydrogen that is directly attached to a fluorine, oxygen, or nitrogen atom, and then that hydrogen would be attracted to an oxygen, fluorine, or nitrogen in another molecule. So not every molecule with hydrogen and oxygen automatically has hydrogen bonding. For hydrogen bonding to occur, the hydrogen has to be bonded to a fluorine, oxygen, or nitrogen. So for example, if we're looking at CH2O, it has oxygen, but its hydrogens are only bonded to the carbon, so it cannot hydrogen bond with itself because that oxygen is not directly bonded to a hydrogen. However, if we mix CH2O with a molecule like methanol, hydrogen bonding can occur because the hydrogens in methanol are directly bonded to oxygen. This graph shows how hydrogen bonding affects boiling points of different hydrides. Normally, as you go down a group, the boiling point is going to increase because of stronger London dispersion forces from those larger, more polarizable electron clouds. But you'll notice sharp jumps for molecules like H2O, HF, and NH3. And those are there because they have very high boiling points due to hydrogen bonding. And because they have hydrogen bonding, it's going to add a significant extra strength to their intermolecular forces. And the only thing I want you to look at on this graph is that NH3 is an exception because SbH3 has a much higher polarizability, and because it has so many more electrons, the LDFs are going to be stronger than the hydrogen bonding in NH3. Here is a brief overview of all the intermolecular forces we went over today. And we're going to end today's lesson with one final example. Looking at these two molecules, we have butanone and N-butane. It says to identify the intermolecular forces in both of them. So in the left molecule, we have an oxygen, but remember it is not directly attached to a hydrogen. So this would just be a polar molecule, which means it has London dispersion forces and dipole-dipole. Then looking at N-butane over here on the right, all we have is carbon and hydrogen. So these are all non-polar bonds, and it is a non-polar molecule. And when you have a non-polar molecule, the only type of intermolecular forces you can have are London dispersion forces. And then B says butanone is much more soluble in water than N-butane. Account for this difference. So remember we talked about in previous slides, even though a sample of butanone cannot exhibit hydrogen bonding, if it's in a sample of water, which has a hydrogen connected to an oxygen, it can partake in hydrogen bonding. So because of that, it's going to be more soluble in water than our non-polar N-butane. All right, I hope this video helped you. If you have any questions, please feel free to reach out and I'm happy to help. I hope you have a great day. Bye.